Hello everyone and welcome to the Ansys tutorial. In the today's session we are discussing stress analysis of bars of constant cross-section area. The problem description is a steel rod subjected to tension is modeled by one bar element as shown in figure. Determine the nodal displacement and the axial stress each element and reaction forces. The Young's modulus is 2.1 10⁵ Newton per millimeter square. The Poisson's ratio is 0.3. Here, as usual, we are creating two nodes here. The node 1 is fixed and node 2 is free. At node 2, we are applying a load of 2500 Newton. The direction of the load is positive because it is moving from left towards right and it is positive. So the given Young's modulus is 2.1 10⁵. The diameter of the cross bar is 60 millimeter. It is a cylindrical shaft. So we have to calculate the nodal displacement at node 1 and node 2 and the stress at the element. The stress is calculated for element. We are creating two nodes. With the help of two nodes, we are making one element. So the stress is for only single element and the displacement, nodal displacement and the reaction forces you have to calculate for particular both nodes, node 1 and node 2. So let's move to the theoretical solution. Given Young's modulus is 2.1 10⁵ Newton per millimeter square. Load is 2500 Newton, positive load. Area of the cross section is we have to calculate, it is not given. So with the help of diameter, which is 60 millimeter, diameter is 60 millimeter. With the help of diameter, we need to calculate the area. We know that the area for cylindrical component is area equals to pi d square by 4. So substitute here, d is 60 millimeter, pi into 60 square divided by 4 will get 2827.433 millimeter square. Next, the deformation. The deformation at node 1 is 0. Why? Because we are considering this as node 1 and this as node 2. The node 1 is fixed here. We can see it is fixed. It will not move with the help of any load. So the displacement will become 0. So at node 1 it is 0 and node 2 you can see it is a free end with this tensile load. This bar will displace with some distance. We have to calculate that change in length. With the help of formula, delta L equals to PL over AE, where P stands for load, L stands for length, A stands for area, E stands for Young's modulus. Substitute all the values which is already given in the problem. P is positive 2500, L is 450, you can see the length is 450, and area we have calculated here 2827. In the Young's modulus which is given 2.1 into 10⁵. We substitute everything, we'll get displacement delta L at node 2 is 1.8947 into 10⁻⁻3, that is nothing but 0.00189 millimeter. Now the stress we have only one element here. The formula for calculating stress is load by area. So load is positive 2500 and the area is 2827.433. You substitute this, we'll get stress as 0.88419 Newton per millimeter square. The next is reaction load. Reaction load is nothing but the forces which is acting opposite to the action load. So the action load here is 2500 Newton at node 2, that is R2. We are considering this as R1 at node 1 and R2 at node 2. We have two reaction. If you add all the reaction, that is R1 plus R2, the total load will become 0. So using this formula, R1 plus R2 equals to 0. We know that R2 equals to 2500 because it is given here. So R1 plus 2500 equals to 0. So if you move this 2500 is this direction, that will become negative. So the R1 will become minus 2500 and the positive R2 is which is given, that is 2500 positive. So these are the theoretical solution. So you have to match all these values in the Ansys. So I'll move to the Ansys software here. I'll go for preference, structural, click on OK. Next I'll go for preprocessor, element type, add, edit, delete. click on add, click on link, select 3D Finet STN 180, click on OK, click close. Next you go for real constant, click on odd edit delete, click on add here. Okay, now you have to fill the area here, that is 2827.43. Now click on OK. Now click close. Now I'll go for material properties, material models, structural, linear, elastic, isotropic. Here you have to fill the two boxes, that is Young's modulus and Poisson's ratio. Young's modulus, it is given as 2.1 exponential to the power 5, and Poisson's ratio is 0.3. Click on OK. To close this. Now go for modeling. Create nodes in active CS. Node number 1, we have two nodes here. Node number 1 at origin 0, 0, 0. All the three values x, y, z should be 0. Click on apply here. Now change the node as 2. You have to change only the x direction, that is lengthwise. You have to write 450, that is our distance from 0 to the node, from 0 to other end, that is 450 millimeter. This is the length of the shaft actually. Click on OK now. You got two nodes, one at origin and one at a distance of 450 millimeter. So now you'll go for creating element. Click on element here, auto numbered, through nodes. Select the first node and select the second node. Click on OK. The line element is created here. Now you have to go for applying loads here. We have two kind of load. One is fixed at node 1, another one is force movement at node 2. For applying fixed at node 1, you have to go for solution, define loads, apply, structural, click on displacement, click on nodes here, on nodes, select the first node, click on OK. Here you need to create, arrest all the movements of the node 1. All degree of freedom should be arrested. Click on all DOF, click on OK, because it is fixed. The node 1 is fixed, which is given in the problem. So you have to fix all degree of freedom, the movement in all the direction. Now you have to apply force movement in the node 2. For that, you click on force movement, click on nodes, select the second node here, click on OK. Now FX direction, positive 2500 is our load. Click on enter 2500. Select OK. Now the load has come, 2500 positive load. If it is negative, the arrow direction will be in the opposite direction. We have positive load here. According to your direction, you have to apply the load. Next, you go for solve current LS. Click on OK. Solution is done. That is everything procedure we have followed is correct. Close, close. Now you go for general post processor. Here you click on element table, define table. This table is defined to calculate the stress. Click on add. Here in the drop down menu, select by sequence number, select LS here. Comma is already there. You just write 1 here, LS comma 1, that is okay. Now close it. Then you go for plot element table, go for plot result here. Plot result. Go for deform shape, deform plus undeformed, okay. You can see the stress value, displacement value here. Contour plot. X component of display, nodal dissolution, in that degree of solution, X component of displacement, okay. You can see the your stress value and everything with the help of diagram here. Now for listing the result, you go for list result, go for nodal solution, x degree of solution, DOR solution, x this component of displacement, click on OK. You can say the displacement, that is 0.189, which is similar to our value. We got 1.89 here, 0. Our value is exactly matching 0.189. It is matching. Now go for nodal loads for showing all items. This nodal loads is for reaction forces. At node 1 it is 2500, at node 2 is minus 2500. This is your reaction load. Next you go for element table data, LS. This is your stress value, 0.88420, which is exactly as 0.88420, which is matching exactly. So all the results are matched with theoretical and Ansys solution. That's it for today's session. Thank you.